Module 9, Lecture A, Graph Basics. By the end of this lecture, you will be able to define basic graph terminology and types, including directed and weighted graphs, implement adjacency list and adjacency matrix representations in Python, and choose appropriate graph representations based on problem characteristics and performance needs. Core graph concept. Graph building blocks. To understand graphs, focus on nodes and edges. A node, also called a vertex, represents an entity such as a person, a city, or a device. An edge represents a relationship or connection between these entities, such as a friendship, a road, or a communication link. When nodes are connected by edges, they form the basic structure of a graph, showing both the components and how they interact. In graphs, both nodes and edges can store extra information that makes the network more meaningful. Nodes might hold details like a person's age or a city's population, while edges can describe the type or strength of a connection, such as how close two people are or how long a road is. These attributes let graphs represent complex systems efficiently by emphasizing relationships instead of rigid tables of data. This structure makes it easier to explore connections, check what is reachable, and understand how information flows through a network. In a graph, nodes and edges form the basic structure, where two nodes are adjacent if an edge connects them. A path is a sequence of edges that links distinct nodes and is important for tasks like finding routes or checking how parts of the graph are connected. The degree of a node is the number of edges attached to it, which helps distinguish highly connected hubs from more isolated nodes. By using adjacency, paths, and degrees, we can describe and analyze complex networks in a precise way. Directed and undirected graphs. In graph theory, the key difference between directed and undirected graphs is whether connections have a direction. In an undirected graph, each edge represents a two-way relationship, so you can move between the connected nodes in either direction without distinction. This makes undirected graphs useful for modeling naturally mutual relationships, such as friendships, or two-way roads. The essential idea is that undirected edges do not go from one node to another. They simply connect the nodes bidirectionally. In a directed graph, or digraph, each edge has a specific direction, so a connection from node A to node B does not automatically mean there is a connection back from B to A. You can think of each edge like a one-way street that only allows movement in a single direction. This structure is important for modeling systems where direction matters, such as social media follow relationships, web links, or course prerequisites. In all these cases, the direction of the edge defines how information, influence, or requirements flow from one node to another. Directed and undirected graphs differ in how they handle connectivity and paths. In an undirected graph, edges work both ways, so if two nodes are connected, you can travel back and forth between them. And connected components are groups where every node is reachable from every other. In a directed graph, edges have a direction, so you may be able to go from one node to another, but not return. And strongly connected regions are the parts where every node can still reach every other. This directional property affects how we model systems like communication networks or project plans, and determines which algorithms and questions are appropriate for analyzing a given network. Edge weights explained. When we add weights to the edges of a graph, we enrich the simple structure of nodes and connections with numerical information about each link. These weights can represent things like cost, strength, capacity, or preference for moving along that edge. In a transportation network, for example, they might show distance, travel time, or fuel cost. And in a communication network, they might indicate bandwidth or reliability. By assigning these values, the graph becomes more than a map of what is connected and turns into a model that helps us compare how desirable or expensive different paths are. In graphs, edge weights represent different quantities depending on the problem, and what counts as better can change. Smaller weights are preferred when they measure things like cost or time and you want the most efficient path. Larger weights are preferred when they represent capacity or reliability and you want to maximize those. Weights can be integers, real numbers, or even infinity to indicate an unusable connection. If all edges share the same weight, the graph is effectively unweighted. But when weights vary, algorithms must account for these differences to make good decisions. Edge weights are crucial in graph algorithms because they let us model not just connections, but how strong or costly those connections are. In logistics, weights on roads between warehouses and stores can represent travel time or cost, helping find efficient delivery routes. In social networks, weights can show how often people interact, revealing strong and weak relationships and helping identify communities. In recommendation systems, weights between users and items, such as ratings or purchase counts, help capture and prioritize preferences. Overall, edge weights turn a simple network into a richer model that supports more nuanced analysis and better decisions. Python graph representations. Dictionary adjacency lists. In Python, a common way to represent a graph is with a dictionary-based adjacency list, where each vertex is a key and its value is a collection of neighboring vertices. This structure is similar to a contact list, with each entry linked to its connections. It matches how many real-world networks, such as social media or transportation systems, are organized. Most importantly, it allows fast lookup of vertices and their neighbors, which is essential for running graph traversal algorithms efficiently. Dictionary-based adjacency lists provide a flexible and efficient way to represent many kinds of graphs. In an undirected graph, each vertex stores the other in its list, allowing movement in both directions. In a directed graph, each vertex only lists its destination vertices, capturing one-way connections. When graphs have weights, such as distances or capacities, these values are stored alongside the connected vertices so algorithms can easily use them during traversal or pathfinding. Dictionary-based adjacency lists are well suited for sparse graphs, where each node connects to only a few others, such as airline routes or research collaborations. They store only existing edges, which saves memory and makes it easy to modify the graph as it changes. For example, adding a new city in a transport network just means creating a new entry and updating its connections. This flexibility makes dictionary adjacency lists a common and efficient choice for large, sparsely connected datasets in Python. Python code, dictionary adjacency lists. Use Python dictionaries to represent simple graphs with adjacency lists, where each key is a node and its value is a list of neighboring nodes. This structure can model both undirected graphs, where connections go both ways, and directed graphs, where edges have a specific direction. By printing each node's neighbors and the list of edges, you can clearly visualize the structure of a small example graph. The commented line mentions installing NetworkX, Matplotlib, and Seaborn, but explains that these libraries are not required for the simple example being shown. This means the code is self-contained and does not depend on external tools. Instead, it relies only on Python's built-in features to demonstrate how to represent a graph using adjacency lists. We begin by creating an empty dictionary to store the graph's adjacency lists. This dictionary will hold all the vertices in the graph as its keys. For each vertex, the corresponding value will be a list of its neighboring vertices. Organizing the data this way lets us efficiently represent and access the connections between vertices in the graph. We begin building the graph by creating a dictionary where each city, labeled A through D, is a key. For every city, we assign an empty list that will later store its neighboring cities. This structure makes it easy to add connections between cities and gradually define the graph's overall layout. To add an undirected edge between two cities A and B in an adjacency list, you update both of their lists. You add B to A's list to show that A connects to B, and you add A to B's list to show the connection goes both ways. This ensures the graph correctly represents a bidirectional link between the two cities. To add an undirected edge between cities A and C using adjacency lists, you must update both lists. Add C to A's list of neighbors to show that A connects to C, and add A to C's list to show the reverse connection. By recording the edge in both directions, you represent that travel is possible both ways between the two cities. In this step, we add a directed edge from city B to city D by placing D in B's list of neighbors in the graph dictionary. This update means that travel or connection is allowed from B to D, but not necessarily in the reverse direction. It represents a one-way relationship in the directed graph structure. Here we add a weighted edge from city C to city D in the graph by appending a pair to C's list of neighbors. This pair includes the destination city, D, and the edge's weight, which is the distance of 120 miles. In this way, the graph stores both the connection between C and D and the cost of traveling from C to D. We begin by printing a short message to let the user know that the full adjacency dictionary of the graph is about to be shown. Then we display the entire graph dictionary, which lists each vertex along with all the vertices it is connected to. This gives a complete picture of the graph structure and makes it easier to see how all the vertices are related. We examine each city in the graph and look up its list of neighboring cities. For every city, we create a short, clear sentence that states which cities it is directly connected to. We then print this sentence so we can easily read and understand the connections. This gives a simple, human-readable view of the graph's adjacency list, showing each city and its direct neighbors. This script shows how to model a simple graph in Python using dictionaries as adjacency lists. It creates 4 vertices named A, B, C, and D, each with a list of neighboring vertices. The code then adds undirected edges between A and B and between A and C by updating both endpoints, and a directed edge from B to D by updating only B. It also demonstrates a weighted edge from C to D by storing both the neighbor and the distance in miles. When run, the script prints the full adjacency structure and a readable list of neighbors for each city, making the graph's connections easy to see. Adjacency matrix basics. An adjacency matrix is a way to represent a graph using a square grid of values. Each vertex is given a unique index, and the rows and columns of the matrix correspond to these vertices. Each entry in the matrix shows whether there is an edge between a pair of vertices, often using 1 to indicate an edge and 0 to indicate no edge. This is similar to listing cities as both rows and columns and marking whether a direct flight exists between each pair. Adjacency matrices are especially useful for weighted graphs because each entry can store the actual weight of an edge, such as distance or cost, rather than just whether the edge exists. In applications like transportation or communication networks, this weight might represent driving distance or available bandwidth. When there is no edge between two vertices, a special value, like 0 or a very large number, is used to indicate its absence. This structure makes it easy and fast to look up the weight of any connection by checking the matrix at the corresponding row and column. In Python, an adjacency matrix for a graph is typically stored as a list of lists, where each inner list represents a row of the matrix. The size of this matrix is fixed by the number of vertices, and its memory use grows with the square of that number. This approach is efficient for small or dense graphs because it allows very fast edge lookups and works well with matrix-based algorithms. However, it can be wasteful for large, sparse graphs since it reserves space for every possible pair of vertices. Choosing this representation requires balancing simplicity, speed, and memory usage for your specific problem. Python code. Adjacency matrix basics. This lesson introduces how to build and use simple adjacency matrices for small graphs. It shows how to represent both unweighted and weighted edges using a list of lists structure. You will see how to print these matrices and perform basic lookups. The goal is to give a clear, beginner-friendly understanding of how adjacency matrices capture connections in a graph. The commented line about installing NumPy, Matplotlib, and Seaborn indicates that these external libraries are optional and not actually used in the script. The code is fully self-contained and runs using only basic Python features. This means it demonstrates adjacency matrices without relying on any additional packages. As a result, learners can focus on understanding the core Python structures involved. We begin by defining a list of 4 vertices labeled A, B, C, and D to represent a small network of flights between cities. Each label stands for one city in the network. Using this list, we can refer to each city by its position, which makes it easier to build adjacency matrices. These matrices will then show which cities are connected by flights. To build an unweighted adjacency matrix, we'll first count how many vertices there are, since this number determines the size of the square matrix. We then create an empty matrix using a list of lists, where each inner list represents a row. Every entry is initially set to 0 to indicate that no vertices are directly connected at the start. The outer list has one row for each vertex, ensuring the matrix is square and matches the number of vertices in the graph. We represent direct flights between cities using an unweighted adjacency matrix, where a value of 1 indicates that a flight exists. To build this matrix, we mark a 1 in the position for the flight from city A to city B. Then do the same for the flight from city B to city C. and finally, for the flight from city C to city D. Each time we assign a 1, we update the matrix to record that there is a direct connection between those two cities. We represent distances between cities using a weighted adjacency matrix, where each row is a city and each entry is the distance in miles to another city. A special value, set to 0, indicates that there is no direct connection between two cities. For example, City A is 500 miles from City B and has no direct route to City C or D, while City B is 500 miles from A, 750 miles from C, and not directly connected to D. City C connects back to B with 750 miles and to D with 300 miles, and City D connects only to C with 300 miles. This matrix format makes it easy to look up and work with distances between any pair of cities. This function prints a labeled view of a matrix. It starts by printing a label that describes the matrix, then builds and prints a header line using the vertex names so listeners know what each column represents. Next, it goes through each row of the matrix using the row index to find the matching vertex name. For each row, it converts the values to strings, joins them with spaces into one line, and prints that line next to the vertex name. The result is a clear, labeled display of the matrix with both rows and columns identified by their vertex names. We first call a function that prints the unweighted adjacency matrix, using a label, the matrix, and the list of vertices as inputs. This function displays the matrix with vertex names as both column headers and row labels, so we can easily see which vertices are connected. After a blank line for separation, we call the same function again to print the weighted adjacency matrix. In this version, the entries include distances in miles as edge weights, giving a more detailed view of the connections while still using the vertex names for clear and consistent labeling. To find the distance between two vertices in a weighted adjacency matrix, you first determine the position of the starting vertex, such as B in the list of vertices. You then do the same for the ending vertex, such as C. Using these two positions, you look up the corresponding entry in the matrix to get the edge weight between them. This lookup takes constant time, and the value you retrieve is the distance from B to C in miles, which you can then report or display. This example shows how adjacency matrices can represent a small flight network with 4 cities labeled A through D. It first builds an unweighted matrix that uses zeros and ones to indicate whether a direct flight exists between each pair of cities. It then creates a weighted matrix that stores the actual flight distances in miles, using 0 when there is no direct connection. The script prints both matrices and performs a constant time lookup to find the distance from City B to City C, which is 750 miles. Overall, it demonstrates how adjacency matrices efficiently store and query both unweighted and weighted graph data. Converting between formats. In Python graph work, you may need to convert between an adjacency list and an adjacency matrix. An adjacency list records which vertices are connected, while an adjacency matrix represents this information in a grid whose rows and columns correspond to vertices. To convert a list to a matrix, first assign each vertex an index. Then fill in the matrix entries to mark where edges exist, including weights if the graph is weighted. This process is similar to turning a list of connections into a structured grid that shows all direct links and their details. To convert an adjacency matrix to an adjacency list, you scan the matrix and rebuild the neighbor relationships for each vertex. First, match each row and column index to its vertex label. Then, for every non-zero entry in a row, add the vertex from that column to the list of neighbors for the vertex in that row, including any edge weights. This produces a more compact representation that is convenient for iterating over neighbors in networks such as social or communication systems. Switching between adjacency lists and adjacency matrices in Python is useful for matching graph representations to different algorithms and performance needs. Adjacency lists work well for sparse graphs, while matrices allow very fast checks of whether two vertices are connected, at the cost of more memory. Being able to convert between these forms lets you choose the right balance of clarity, speed, and memory for each graph-related task. Python code: converting between formats. This lesson focuses on converting between two common graph representations, adjacency lists and adjacency matrices. You will work with a simple unweighted directed graph and practice transforming it from a list format to a matrix format and back again. Both representations should be printed in a clear, easy-to-read way so that beginners can understand how they relate. If needed, you may install any required library before performing these conversions. We represent a directed graph using a small adjacency list stored in a dictionary. Each key is a vertex, and its value is a list of vertices that it has edges to. For instance, one vertex can point to two others, another can point to one of them, and a third can point back to the first. This structure makes it easy to see which nodes are connected and in which direction the edges go. We begin by creating a list of vertices from the adjacency list and then sort this list. Sorting ensures the vertices always appear in a consistent, predictable order. This consistent ordering is important when converting between different graph representations. It gives us a stable sequence of vertex labels to use in all later steps. We build a dictionary that links each vertex label to its index in the adjacency matrix. To keep the order consistent, we first sort the list of vertices and then assign each one an index. This way, every vertex is paired with a unique position in the matrix. This mapping is essential because it lets us easily convert between an adjacency list and an adjacency matrix by translating vertex labels into matrix indices. To build the adjacency matrix, we first count how many vertices are in the graph, which tells us the size of the matrix. We then create an empty two-dimensional list with that many rows and columns and set every entry to 0. This matrix is large enough to represent all possible connections between vertices. Later, we will replace specific zeros with ones wherever an edge exists, converting the adjacency list into matrix form. To build the adjacency matrix from an adjacency list, we go through each source vertex and examine its list of neighbors, which represent directed edges. For every neighbor of a given source, we update the matrix entry at the row for the source and the column for the neighbor. We set that entry to 1 to indicate that there is a directed edge from the source vertex to the destination vertex in the graph. Repeating this for all vertices and their neighbors fills in the entire adjacency matrix. We begin by creating an empty adjacency list to rebuild the graph from its adjacency matrix. Each vertex is added as a key, and its value is an empty list that will later hold its neighbors. This setup ensures we have a structure ready to record all connections between vertices. As we scan through the adjacency matrix, we will fill in these lists so the final adjacency list accurately reflects the original graph. To rebuild an adjacency list from an adjacency matrix, we loop over each vertex using its index to select the corresponding row of the matrix. For each source vertex, we then loop over all vertices again to examine each column in that row. Whenever an entry in the matrix is 1, it means there is an edge from the current source vertex to that destination vertex. We then add that destination vertex to the source vertex's list of neighbors. Repeating this for all vertices reconstructs the full adjacency list representation of the graph. We begin by printing the original adjacency list, so we have a clear reference for the graph's structure. This reference lets us compare the initial representation with any reconstructed versions after converting between different graph formats. By checking that the printed adjacency list matches the one we rebuild later, we can confirm that the conversion process preserved the graph correctly. We begin by printing a header to show that we are displaying the adjacency matrix, along with the vertex labels for clarity. Then we print the vertex labels again as a header row, so each column can be matched to a specific vertex. After that, we go through each row of the matrix, printing the corresponding vertex label followed by the row values. This layout makes it easy to see which vertices are connected, since a value of 1 indicates a directed edge from the row's vertex to the column's vertex. We print the reconstructed adjacency list to confirm that converting from the adjacency matrix back to the list format worked correctly. By checking this output, we verify that the transformation preserved the original graph structure. This step helps ensure that no connections were lost or changed during the conversion process. This script shows how to convert a directed graph between an adjacency list and an adjacency matrix. It starts with a graph described as a list of vertices and their neighbors, then sorts the vertices and assigns each one an index. Using this index mapping, it builds an adjacency matrix filled with zeros and sets entries to 1 wherever there is an edge. The script then reverses the process by scanning the matrix to reconstruct the adjacency list. Finally, it prints the original list, the matrix with vertex labels, and the rebuilt list to confirm that the conversion in both directions is accurate. Graph representation trade-offs. Memory usage trade-offs. When choosing how to represent a graph in a program, it is important to think about how memory use grows as the graph gets larger. An adjacency matrix reserves space for every possible connection between vertices, so its memory usage increases very quickly as you add more vertices. An adjacency list, on the other hand, only stores the edges that actually exist, so its memory use grows with the number of real connections. This makes adjacency lists generally more memory efficient for large or sparse graphs, which is crucial when managing resources in applications with changing graph sizes. In a large social network where each person connects with only a few others, using an adjacency matrix wastes memory because it reserves space for every possible pair, most of which are not real connections. An adjacency list is more efficient because it stores only the actual relationships, such as friendships or professional contacts. This makes it a better match for networks that are mostly sparse. The same idea applies to other systems with few connections, like roadmaps or recommendation systems. An adjacency matrix can be a good choice when most vertices in a graph are connected, so the number of actual edges is close to the maximum possible. In these dense networks, such as some data center or machine learning graphs, the extra memory cost is relatively small, and the fast access benefits can be worth it. When designing a system, you should think about how many vertices and edges you expect and how this might grow over time to decide whether an adjacency matrix or another representation will be more efficient. Python code, memory usage trade-offs. We compare memory usage between adjacency matrix and adjacency list representations of graphs by building small example graphs and estimating how much space each approach needs. An adjacency matrix stores all possible connections between nodes, which can waste memory when the graph is mostly empty. In contrast, an adjacency list stores only the actual edges, making it more efficient for sparse graphs with few connections. As graphs become denser and contain many edges, the matrix representation wastes less space and can become more reasonable. To support these experiments programmatically, you may first need to install the numerical computing library NumPy. We begin by importing the system module, which lets us access system-level information, such as the memory size of Python objects. We also import the numerical computing library NumPy, which allows us to create and work with arrays efficiently. With these tools in place, we are prepared to examine how much memory different graph representations use. This function estimates how much memory an adjacency matrix will use for a given number of vertices. It first finds how many entries the matrix has by multiplying the number of vertices by itself, since every vertex can connect to every other vertex. It then assumes each entry uses 1 byte of memory. Finally, it multiplies the number of entries by this byte size to return the total memory usage. This description explains how to estimate memory usage for a graph stored as an adjacency list. The function takes the number of vertices and edges as input. Each vertex list is assumed to use 16 bytes, and each edge entry uses 8 bytes. To get the total memory estimate, it multiplies the number of vertices by 16, multiplies the number of edges by 8, and then adds these two results together. The compare memory function reports how much memory is used by two different graph representations for a given number of vertices and edges. It first estimates the bytes needed for an adjacency matrix using only the vertex count. Then, it estimates the bytes needed for an adjacency list using both the vertex and edge counts. After that, it prints a short description of the scenario, the numbers of vertices and edges, and the calculated memory usage for each representation so you can clearly compare them. We model a typical social network as a sparse graph by first choosing 1,000 vertices, which represent entities such as people or intersections. We then set the number of edges to 10 times the number of vertices, meaning each node connects to about 10 others on average. Because this number of edges is small compared to all the possible connections between vertices, the resulting graph is considered sparse. We define a dense communication network as a graph with 1,000 vertices, each representing a node in the network. To find the maximum possible number of edges in a fully connected version of this graph, we consider every possible pair of vertices. Each pair can be connected by one edge, and we divide the total number of ordered pairs by 2 so that each edge is counted only once. This gives the standard formula for the maximum number of edges in a fully connected graph with a given number of vertices. To estimate the number of dense edges in a graph, we first find the maximum possible number of edges in a fully connected graph using the standard combination of 2 vertices. We then take about 90% of this maximum to approximate a dense edge count. This method simulates a dense graph where most potential connections are present, giving a realistic representation of a highly connected network. We use a function to compare how much memory different graph representations use for a sparse graph, one with many vertices but relatively few edges, like a city social network. The function takes the number of vertices and edges as input, and then calculates the memory required for both an adjacency matrix and an adjacency list. It prints the memory usage for each representation so we can see how they differ. This helps us understand the memory trade-offs between these two approaches in a sparse graph scenario. The code calls a function that compares memory usage for a dense graph representing a data center-style communication network. Using the previously defined numbers of vertices and edges, the function reports these values and estimates how many bytes are needed for both an adjacency matrix and an adjacency list. By printing these results, it shows how memory requirements differ between the two representations when the graph is dense. To compare the memory usage of different graph representations, we start with a very small graph of 5 vertices. This simple setup lets us build both an adjacency matrix and an adjacency list for the same graph. We can then measure how much memory each representation uses in Python. This concrete example helps us understand how their memory consumption behaves and what might happen when we scale up to larger graphs. We use a numerical library to create an adjacency matrix for a small graph, starting with all entries set to 0 to represent no edges between any vertices. The matrix size is based on the number of vertices, so with 5 vertices, we create a 5 by 5 matrix. Each entry indicates whether a connection exists between a pair of vertices. We store the values as 8-bit integers to save memory, since each entry only needs to record a simple on or off connection state. We build an adjacency list for a small graph in Python by using a dictionary where each vertex is a key. For every vertex, numbered from 0 up to 1 less than the total number of vertices, we start with an empty list. These lists will later hold the edges connected to each vertex. This structure is efficient for storing and working with sparse graphs, where most pairs of vertices are not directly connected. We begin by explaining that the goal is to compare how much memory 2 graph representations use. Using a system utility, we measure the size in bytes of a small graph stored as an adjacency matrix. We then measure the size in bytes of the same graph stored as an adjacency list. Comparing these two values shows the memory trade-offs between the matrix and list representations for small graphs. This script compares how much memory adjacency matrices and adjacency lists use when representing graphs. It estimates memory needs for a sparse graph, like a social network, and a dense graph, like a communication network. For a sparse graph with many vertices but relatively few edges, the adjacency list is more efficient. While for a dense graph with a very large number of edges, the adjacency matrix becomes more practical. The script also builds a small 5-vertex example in Python using a NumPy-based matrix and a dictionary-based list, then prints their memory sizes. Overall, it shows that adjacency lists are better for sparse graphs, whereas adjacency matrices are preferable for dense graphs. Neighbor traversal efficiency. To evaluate how efficiently you can traverse neighbors in a graph, you focus on how quickly you can access all vertices directly connected to a given vertex. With an adjacency list, each vertex stores a list of its neighbors, so you can easily iterate through them. This is useful for algorithms that need to find all vertices reachable in one step, such as quickly listing a user's friends in a social network. In this setup, the traversal cost depends mainly on how many neighbors that vertex has, not on the total number of vertices in the entire graph. An adjacency matrix represents connections between vertices in a grid, which makes it very fast to check whether a specific edge exists by looking directly at the corresponding cell. However, finding all neighbors of a vertex is inefficient because you must scan an entire row or column, even if there are only a few actual connections. In a large, sparse transportation network, this means listing all cities reachable from one city requires checking every possible city. As a result, the time to find neighbors depends on the total number of vertices, not just the number of direct connections, making adjacency matrices less efficient for sparse graphs. When choosing how to represent a graph, focus on the algorithms you will run and how dense the connections are. Adjacency lists work well when each vertex has few neighbors because they only store and traverse existing edges. Adjacency matrices can be better for dense graphs since they allow very fast checks of whether an edge exists, even though scanning rows is more costly. Overall, balance how often you need to traverse neighbors, how many connections there are, and how important quick edge presence checks are when deciding between these representations. Python code, neighbor traversal efficiency. We want to compare how efficiently we can scan the neighbors of a vertex using two graph representations, the adjacency list and the adjacency matrix. In an adjacency list, the time to find all neighbors of a vertex depends only on how many neighbors that vertex actually has. In contrast, with an adjacency matrix, the time to scan for neighbors depends on the total number of vertices in the graph. Because we must check every possible connection, this demonstrates that neighbor traversal efficiency is tied to different factors in these two representations. This line in the script is simply a placeholder to remind you to install any extra libraries that are not part of the standard Python library. In this particular script, only standard libraries are used, so you do not need to install anything additional. Its main purpose is to prompt you to check that all required dependencies are available before you run the code. we define a function that builds an adjacency list representation of a graph using the number of vertices and the desired number of neighbors per vertex. It starts with an empty dictionary and, for each vertex, creates an empty list to store its neighbors. For each required neighbor, it computes the neighbor's index by adding the current vertex index, the neighbor position, and 1. Then taking the remainder when divided by the total number of vertices, so that indices wrap around. Each computed neighbor is added to the vertex's list. The function then returns this dictionary as the completed adjacency list describing the graph's connectivity. To build an adjacency matrix for a graph, we start with a square matrix of zeros, whose size matches the number of vertices. This matrix will record which vertices are connected. For each vertex, we loop over a fixed number of neighbors and compute each neighbor's index by adding the current vertex index and the neighbor offset, then wrapping around using the total number of vertices. We then set the corresponding entry in the matrix to 1 to mark a connection. After processing all vertices and their neighbors, the completed matrix represents all edges in the graph. This function finds all neighbors of a given vertex using an adjacency list. It begins by creating an empty list, then goes through each neighbor linked to that vertex in the adjacency list. As it visits each neighbor, it adds it to the list. In the end, it returns this list, efficiently collecting all direct neighbors of the vertex. This function finds all neighbors of a chosen vertex in a graph that is stored as an adjacency matrix. It first prepares an empty list to hold the neighbors, then uses the size of the matrix to know how many vertices there are. It checks each possible vertex to see if there is a direct connection from the chosen vertex, which is indicated by a 1 in the matrix. Every vertex that is connected in this way is added to the list. And the function finally returns this list of all directly connected vertices. In this script, we import the time module to access functions that work with time. We use it to record when specific parts of the code start and finish running. By comparing these start and end times, we can calculate how long each operation takes. This timing information is essential for evaluating and comparing the efficiency of different graph traversal methods. We set up a graph to model a sparse social network by first choosing 1,000 vertices, which represent the nodes in the network. Each vertex is connected to 5 neighbors, giving the graph relatively few connections per node, similar to many real social networks. We also select vertex 0 as the starting point for exploring or traversing this graph. We build 2 graph representations using the same connectivity pattern, so we can later compare how efficiently they let us traverse neighbors. First, we create an adjacency list using a function that takes the total number of vertices and the desired number of neighbors per vertex and returns a dictionary mapping each vertex to its list of neighbors. Then, we create an adjacency matrix with a similar function that returns a 2-dimensional list, where each row is a vertex and each column indicates whether it is connected to another vertex. These 2 structures capture the same graph, but in different forms, setting up a fair comparison of their performance. To measure how long a neighbor traversal takes, we first record a precise start time using the performance counter from the time module. We then run the function that traverses the neighbors of a given vertex using the adjacency list representation, which returns the list of neighbors. After the traversal finishes, we record the time again with the performance counter. Finally, we subtract the start time from the end time to find the total duration of the traversal. To measure how long neighbor traversal takes with an adjacency matrix, we first record the current time using a high-precision performance counter. We then run the function that finds all neighbors of a given start vertex using the adjacency matrix representation. After the traversal finishes, we record the time again with the same counter. By subtracting the start time from the end time, we obtain the total traversal time, which tells us how efficient the adjacency matrix approach is for this task. We first display the neighbors of a starting vertex, found using the adjacency list, then report how long this traversal took by subtracting the start time from the end time. This shows which vertices are directly connected and gives a sense of how efficient the list representation is. We then do the same using the adjacency matrix, printing the neighbors it finds and the time required. Comparing these times highlights that the adjacency list only examines actual neighbors, while the adjacency matrix checks every possible vertex, leading to different traversal efficiencies. This script compares how efficiently a graph's neighbors can be traversed using adjacency lists versus adjacency matrices. It builds a sparse graph with many vertices, but only a few neighbors per vertex, then measures the time needed to visit neighbors starting from one vertex with each representation. With adjacency lists, the traversal is faster because it directly accesses only the actual neighbors. With adjacency matrices, it is slower because it must scan all possible vertices to find which ones are connected. The results show that adjacency lists are generally more efficient than adjacency matrices for sparse graphs. Sparse graph choices. For sparse graphs, where there are few edges compared to all possible connections, choosing an efficient representation is important. In situations like a social network with few friendships or a transport map with limited direct roads, adjacency lists work well. They store only the edges that actually exist, instead of reserving space for every possible connection. This saves memory and keeps the structure compact and efficient. Sparse graphs are efficient because they store and process only the edges that actually exist, which saves memory and speeds up operations. When you explore neighbors or find shortest paths, you only need to look at real connections, not every possible pair of nodes. Adjacency lists are well suited for this, since their size grows with the number of edges instead of all node pairs. In cases like airline routes, where each airport connects to only a few others, adjacency lists let you work directly with the real flights, making them ideal for sparse graphs. When representing sparse graphs, choose a structure based on the queries you run most often. An adjacency matrix lets you check for the existence of an edge very quickly, but it uses a lot of memory and is inefficient for very sparse graphs. Adjacency lists and other sparse formats, such as sorted arrays or hash-based sets, use memory more efficiently and can improve cache performance, though edge checks are slower. For large systems, like recommendation engines or web graphs, these list-based methods are usually preferred. Overall, you should match the graph representation to how densely the graph is connected and which operations you need to support efficiently. Python code, sparse Graph choices. We will compare how sparse graphs are represented using adjacency lists and adjacency matrices and see how these choices affect efficiency. In particular, we will look at how much memory each representation effectively uses when the graph is sparse, with relatively few edges, versus when it is dense, with many edges. We will also examine how the work required to traverse neighbors in a graph scales with the actual number of edges, rather than with all possible pairs of vertices. Together, these ideas show why adjacency lists are often preferred for sparse graphs, while adjacency matrices may be more suitable for dense ones. The installation line for NetworkX, Matplotlib, and NumPy is commented out because these libraries are already available in the Colab environment. As a result, the code can run without any extra installation steps. This approach makes the notebook easier to use and share, since others do not need to set up these common libraries manually. It is a standard practice when working in environments that pre-install popular packages. The code uses the default class from the collections module to create a special kind of dictionary that automatically supplies a default value when a key does not exist. This is especially helpful when building adjacency lists for graphs because new entries can be added without extra checks. With default, the program does not need to test whether a key is already present before reading from or writing to it, which simplifies the code and reduces errors. We define a function that builds an adjacency list to represent a graph. It takes the number of nodes and a list of edges as input. Using a special dictionary that automatically creates empty lists, we go through each edge and add the destination node to the list of neighbors for the starting node. The result is an adjacency list that efficiently stores only the actual connections in the graph. This function builds an adjacency matrix to represent a graph. It first creates a square matrix of zeros where the size is based on the number of nodes. Each position in the matrix corresponds to a possible connection between two nodes. Then, for every edge in the edge list, it updates the appropriate position in the matrix to 1 to indicate a connection. The use of nested lists makes the matrix structure clear and easy to work with. This function estimates memory usage for two ways of storing a graph, an adjacency list and an adjacency matrix. It first counts how many connections are stored in the list by adding up the lengths of all neighbor lists for every node. Then it computes how many entries are in the matrix by multiplying the number of rows by the number of columns, which represents all possible connections. Finally, it returns both counts so you can compare the storage requirements of the list and matrix representations. This function estimates the work needed to traverse neighbors of a start node in a graph using two different representations. With the adjacency list, it counts how many neighbors the start node has by taking the length of its list, which reflects only actual connections. With the adjacency matrix, it uses the length of the row for the start node, which represents all possible connections, whether they exist or not. It then returns both counts, so you can compare the traversal effort between the adjacency list and the adjacency matrix. In this example, we set the number of nodes to 100, representing entities such as airports, your cities, in a simplified transportation network. The node count is important because it determines the overall size of the graph. This, in turn, affects how we model and analyze the connections between these entities, whether the network is relatively sparse or highly dense. We build a sparse graph by giving each node exactly 2 connections, forming a simple ring. Using a list comprehension, we loop through all nodes from 0 up to the total number of nodes. For each node, we connect it to the next node in sequence. A modulo operation wraps the last node back to the first, completing the circular structure and keeping the graph sparse. To make the graph more realistic, we add long-distance connections on top of the sparse edges. We do this by visiting every 10th node and linking it to the node that is 10 positions ahead, wrapping around to the start when needed so we stay within the total number of nodes. This creates additional long-range links between nodes. As a result, the graph better reflects real-world networks where each node can have both nearby and distant connections. We build a list of dense edges by looping over all nodes and recording directed connections between them. For each node treated as the current node, we loop over all nodes again as potential neighbors. We only add an edge if the neighbor is not the same as the current node to avoid self-loops, and if its index is less than the current node's index plus 10. So each node connects mainly to nearby nodes. This creates a dense graph where each node has many outgoing edges, but the graph is not fully connected to every possible node. To represent a sparse graph, we first build an adjacency list using a function that takes the total number of nodes and the list of edges. This function creates a mapping from each node to a list of its neighboring nodes, showing which nodes are directly connected. It typically uses a default dictionary to store these neighbor lists. This adjacency list structure is efficient for sparse graphs because it records only existing connections, using less memory than representations like adjacency matrices. To build the adjacency matrix for a dense graph, we use a function that takes the total number of nodes and the list of edges, though it uses more memory than an adjacency list. We build an adjacency list for a dense graph by calling a function that takes the total number of nodes and the list of dense edges as inputs. The resulting structure, stored as a dense list, records which nodes are connected to each other. This representation is important because it efficiently captures all the connections in the dense graph. With this adjacency list in place, we can later analyze the graph and compare its properties to other ways of representing the same network. We use a function to build an adjacency matrix for the dense graph. It takes the number of nodes and the list of edges, then starts with a matrix filled with zeros to represent no connections. For each edge, it updates the corresponding entry in the matrix to 1 to show that those 2 nodes are connected. This matrix form makes it easier to study the structure of the dense graph and understand its storage requirements. We estimate how much memory is used by sparse and dense graph representations by counting stored entries in each. A function measures how many connections are actually stored in the adjacency list and how many possible connections are stored in the adjacency matrix for the sparse graph. This comparison shows the difference in storage needs between the 2 approaches. The counts are then saved for later analysis of their memory efficiency. To measure storage usage for dense graph representations, we use a function that counts how many entries are stored in both the adjacency list and the adjacency matrix. We pass the dense graphs list and matrix into this function, and it returns 2 numbers, one for the list and one for the matrix. These counts indicate how much memory each representation requires for the same dense graph, allowing us to compare their storage efficiency. We begin by choosing a starting node in the graph, which in this example represents an airport, and use it as a reference point for exploring how we visit neighboring nodes. This fixed starting point lets us directly compare how neighbor traversal behaves in different graph representations. It is especially important when we want to evaluate and contrast the efficiency of traversing sparse graphs versus dense graphs. To analyze traversal work in a sparse graph, we use both its adjacency list and adjacency matrix. A neighbor traversal function is called with the sparse graphs list and matrix, along with a starting node. This function returns how many steps it takes to visit all neighbors using the list and how many steps it takes using the matrix. Comparing these two step counts shows how traversal complexity differs between the two representations in a sparse graph. We measure how many steps it takes to visit neighboring nodes in a dense graph using two different representations, an adjacency list and an adjacency matrix. A traversal function is called with the dense graph in both forms and a chosen starting node. It returns the number of steps needed for neighbor traversal with the list and with the matrix. Comparing these two values shows how the amount of work in traversal scales differently depending on which graph representation is used. The code prints a brief summary of how much storage a sparse graph uses in two different forms. It reports the number of entries in the adjacency list, then the number of entries in the adjacency matrix for the same graph. By comparing these two numbers, you can see how storage requirements differ between list and matrix representations of a sparse graph. The code reports how much storage is used by two ways of representing a dense graph. It prints the number of entries in the adjacency list and in the adjacency matrix for the same dense configuration. By comparing these counts, you can see how their memory requirements differ when many nodes are heavily connected. This line reports how many steps it takes to visit neighboring nodes in a sparse graph using two different representations, an adjacency list and an adjacency matrix. It starts from a chosen node and counts the traversal work required in each case. By comparing these step counts, it highlights how efficient each representation is for exploring neighbors in a sparse graph. This line reports how much work is required to traverse a dense graph using two different representations, an adjacency list and an adjacency matrix. It prints the number of steps needed to visit all neighbors starting from a chosen node in each case. By comparing these step counts, it highlights how the list and matrix approaches differ in computational effort for the same traversal task. A final line of the code explains how adjacency lists and adjacency matrices scale differently as a graph grows. Adjacency lists increase in size only with the number of actual edges, so they are efficient for sparse graphs. Adjacency matrices, however, scale with all possible connections between nodes, which can be wasteful for sparse graphs but suitable for dense ones. This line emphasizes that you should choose the graph representation based on how dense or sparse the graph is. This script compares how adjacency lists and adjacency matrices handle memory and traversal in sparse and dense graphs. In a sparse graph, where each node has only a few neighbors, adjacency lists store only existing edges, so they use much less memory and require fewer steps to traverse neighbors from a starting node. In a dense graph, where nodes have many connections, the storage difference between lists and matrices becomes smaller, and traversal steps are more similar. Overall, adjacency lists scale with the actual number of edges, while matrices scale with all possible connections, making lists more efficient for sparse graphs. In this lecture, you learn to define basic graph terminology and types, including directed and weighted graphs, implement adjacency list and adjacency matrix representations in Python, and choose appropriate graph representations based on problem characteristics and performance needs. In the next lecture, Lecture B, we will go over BFS and DFS. Thank you for your attention. See you all in the next lecture.